So in this video, I'll be implementing some major components of Quicksort. So we start off with this recursive Quicksort method function. It takes an array, it has a start index and an end index. This assumes that some kickoff method calls this where the start index is 0 and the end index is the last element of the array. But once we're in here, this is the recursive Quicksort procedure that calls itself. Now, I'm going to be doing the fully optimized version, which does insertion sort on small subarrays. And so I'm going to first compare the size of the subarray. And so I calculate that as end minus start plus 1, because, if you think about it, if I have an array with a start index of 2 and an end index of 3, so this is a subregion of that array, there's really 3 elements here. And so if I want to count the size of that subregion, I add 1. Now, as long as this is less than some min size, which, this would be defined elsewhere as being 3. So in this case, we're going to do insertion sort. Now, it is very important that you only do insertion sort on the elements from start to end. So that means we're assuming that there exists some version of insertion sort that takes the array, but also takes these parameters, start and end. And, there could be all kinds of elements in that portion of the array. But if I call insertion sort with array 0, 2, it's only going to sort these elements and not touch these ones at all. So we don't want to sort the whole array, because sorting the whole array every time we hit a base case would be very inefficient. So we'll close this off, and then we'll worry about the recursive case, which is where Quicksort is really interesting. So the implementation of Quicksort is going to assume that we have a helper method named partition that will split the elements up according to whatever the pivot is. So partition will both select the pivot and then partition the elements on either side of it. So a lot of work is happening here, and we will look at this in a moment. But for now, we're just going to call partition with the array and the range that we're sorting, so start and end, and assume that this takes care of the whole partitioning process. But what it does is it returns pivot, which is an index. So this index is the location in our subarray around which everything is partitioned. So if this is where the pivot is, then the value returned here is the index, and we know that everything here is less than the pivot, and that everything on the right side is greater than the pivot. So the pivot is the index in the array around which we're partitioning things. And so that means that all that's left to do is recursively sort the left half and recursively sort the right half. So I will call Quicksort here on the left half. That means I'm sorting from the start index up to the position right before the pivot, so pivot minus 1. And then to sort the right half, I call Quicksort from pivot plus 1, because that's the position immediately to the right of it, and that'll go all the way up until the end. Close that. Close the procedure. And that's it. We get the pivot, and then we sort things to the left of it and sort things to the right of it, and we're done. All that's left is to define this fairly complicated partition procedure. So that is what's coming next. So this part of the implementation will involve a bit more pseudocode than the previous one, but it will give the broad strokes of the partition procedure. So we are still doing median of 3 pivot selection, and that means I need to know where the midpoint is. So once I have the index of the midpoint, I am going to use some procedure named sort first, middle, last that looks at those 3 positions and it will reorganize them so that those 3 at least will be in order. So I'm not going to provide the full definition of this, but I will say that if you have an array like this, where you have your start, your midpoint, and your last index, you can look at these 3 positions, and it only takes a small number of direct comparisons to figure out, like, for example, if we have a 10 here and a 3 here and a 7 here, that's not in order. But what I can do is look at these 2, compare the 10 and the 3, realize 3 is smaller, and swap them. And then I can look at the 10 and the 7, realize that 7 is smaller, and swap them. And then just double check that 7 is in fact greater than 3. It is, therefore it'll stay there. And now I've organized at least these 3 elements in order with respect to each other. There's still other elements between those that could be anything, but I know that those 3 are in order. And more importantly, this index is still the midpoint. So what I'm going to do with that is I'm going to move this element to the near the end of the array for safekeeping. So I'm going to swap the positions of the midpoint and the index right before the end, so n minus 1. So there's some element here. It could be anything. I'll just put an x. And I want to swap those 2. And the reason I did that is because I'm going to have to reorganize all the elements between here and here. And I need to be able to put this pivot somewhere for safekeeping. I'll put it in its proper location later. But for now, I just want to get it out of the way. Now I want to remember that this is here, so I'll define the pivot index to equal the location where it's at, n minus 1. And for the sake of convenience, I'll store the actual value because I'm going to be comparing it to other elements quite a lot. And so it's useful to just store it in its own variable. Now the goal at this point is to partition this remaining area between that first element and the pivot index. So I want to start from here on the left and then start from here on the right and then work towards the middle, organizing elements as appropriate. So that means I have a variable that is looking at things from the left and a variable that's looking at things from the right. Now notice that because I put the pivot here, that my starting point on the right is actually 2 positions before the end index, hence the minus 2. Next, I'm just going to define a variable done that's false, and then loop as long as I'm not done. So while not done, do the following. So the goal here is going to be to look for an element on the left side that doesn't belong there, and look for an element on the right side that doesn't belong there. And if we find them, then we'll swap them, and then we'll move one step inward from that swap, and then continue the process until we eventually meet in the middle and we're done. So we have a loop here. Inside of this, we have another loop. And I'll simply say that we increase from left while the value at that index is less than the pivot. And so that's this moving to the right portion. Similarly, we will decrease from right as long as the value in the array at that index is greater than the pivot. So each of these is handled by its own separate subloop. And once we've found an element from the left that is not small enough and an element from the right that is not large enough, we then see where they're located, because we're moving from the left and from the right. And if it turns out that the left side and the right side haven't crossed yet, then we need to swap things over. So we only do this swap if the index from left is less than the index from right. We will both swap the elements, and this means those positions in the array, but then we'll also increase from left and decrease from right. That's what these little jumps there represent. So that's what we do if the from left and the from right haven't crossed yet. If they have crossed, meaning that this went until it found some large element there, and this went until it found some small element here, well, then the elements that were just found are already in the proper partition. So that means we're done. So we say that we're done. And this means that our loop can end. That's this loop here. But the partition isn't quite finished yet, because remember that we moved our pivot right here for safekeeping earlier. We've got to put it back in place, but where exactly is that? And then we also need to return the index of where it's located now in the partitioned array. So to get this back in place, we actually swap the pivot index, which is over here. It's just end -1. And we swap it with the index from the left. So that will end up putting it in the right spot. And so at this point, the pivot index is no longer the actual index where the pivot is. The pivot is now located at from left. And so we can end this simply by returning from left, because this is the location that's needed all the way back up here in Quicksort in order to define this value to make the rest of this work. So the partition part of Quicksort is quite complicated. That's really where the challenge in the implementation is. The recursive portion up here is quite elegant, but in the partition, there's lots of room for mistakes, and I recommend looking at this very carefully if you plan to implement Quicksort based on this pseudocode.